So in this video, I'm going to give a class on communication. Now, communication can mean a lot of different things: verbal commands, hand signals, smoke signals. But from what I've seen, unless it's your specific job, radio communication isn't something that's prioritized in training, besides maybe programming a frequency into a radio. As you progress through the ranks, using a radio becomes a bigger and bigger part of your job, whether it's reporting information, requesting resources, or calling for help. Eventually, instead of being the person doing the fighting, you become the person coordinating the fight. Now, mountainous terrain can split groups up into smaller forces that need to act more independent. That's why I think it's important for everyone to at least have a base of knowledge about what a radio is, what radios we have, and when we use them. Now, this is an old radio class that I taught as a baseline. It's a little oversimplified, but these are concepts that we need to understand first before we get into some more advanced topics. And the first thing we're going to start with is, what is a radio wave and how is it measured? So here's an example of an electromagnetic wave. So you can see it goes up in amplitude by 1 unit and then down in amplitude by 1 unit, and then it completes its cycle. That's called a sine wave. The number of cycles it does per second is the number of hertz it is. So in this example, it's 5 cycles per second, so it's 5 hertz. When we're talking radio waves, we're talking about very fast frequencies. So we're talking about kilohertz, megahertz, gigahertz. Kilo, just like any metric unit of measurement, is 1,000 hertz, so 1,000 cycles per second. Then megahertz is 1,000,000 cycles per second, and then gigahertz is 1,000,000,000 cycles per second. So here we have a little bit wider view of the electromagnetic spectrum. To the left off the graph, in lower frequencies, that's going to be stuff that we can hear with our human ears. But then when you get to 3 kilohertz to 3,000 gigahertz, that's going to be what we consider radio frequencies, which we'll talk about more in a second. And then as you go farther right in the graph, you can see things like infrared, visible lights, so stuff we can see, and then ultraviolet, and then we're going to get to radiation waves like X-rays, gamma rays. Okay, so now we have a little bit zoomed in view of the radio frequency spectrum. And it's going to sound a little counterproductive, but HF, which stands for high frequency, is going to be the lowest frequency that we typically talk on a radio. From HF, we then have VHF, which is very high frequency, and then UHF, which is ultra high frequency. So here's the range in which these categories fit into. So high frequency is going to be anywhere from 3 to 30 megahertz, and that wavelength is going to be between 120 meters and 10 meters. So now it's a little bit inverse, where the higher the frequency, the lower the wavelength. VHF is 30 kilohertz to 300 kilohertz, and that's going to be 10 meters to 1 meter. And then UHF is 300 megahertz to 3,000 megahertz, or 3 gigahertz. So why does all this sciencey stuff matter? On this graph, you can see that we have HF, VHF, and UHF from top down. On the HF wave, you can see how long it takes, relatively long it takes for it to complete one cycle, and that's why the wavelengths are actually longer even though the frequency is lower. Well, HF I like to think of like you're walking, right? You can walk for a long time because it takes a little bit of energy to walk. But it's hard to walk through an obstacle. Like, you can't walk through a brick wall. But you can walk for a long distance. And that's how I think of HF. It's for long distance communication. VHF is like you're jogging. You can't jog as far as you can walk because it takes more energy to jog, but you could also push through more obstacles, right? This is best for outdoor communication. UHF is like you're sprinting. You could sprint. You can't sprint as far because you're using a lot of energy, but you can easily run through obstacles. Best way to think about this is best used for indoors obstructed communications, to penetrate concrete walls or obstacles that these waves need to get through. Okay, so assuming all equipment is equal, let's compare the different ranges of different frequency bands. So the first one is we have half a watt. Half a watt is the power on UHF, so ultra high frequency. On flat open terrain, half mile to 2 miles. Suburban, so broken terrain, you have a little bit less because there's more obstacles in the way, maybe houses, maybe trees. And then you have urban areas. That's going to be concrete buildings, things that can get in the way of the radio waves. And you can see that that's only a quarter mile to half a mile. Now when we get to inside buildings, again, that's even more dense. Now we're counting in floors, not miles. So that's 3 to 5 floors. But you can see once we double the power, so we go from half a watt to 1 watt of power, that can potentially double the range of how far we can talk in flat open terrain, and same with everything else. Now, when we get to 2 watts, we can see a pretty close comparison of UHF to VHF. You can see flat open terrain, VHF can talk a little bit farther, but then when you get to inside buildings, UHF has a little bit easier time penetrating concrete walls and floors and things like that. For an even bigger comparison, you can then double that power to 4 watts. Again, flat open terrain really doesn't make much of a difference, flat open terrain, but then when we get to suburban locations, obstacles getting in the way, you can see that UHF is starting to pull ahead a little bit. Urban areas, again, 3 miles on the upper end compared to 2 miles, and inside buildings penetrates better, so that's maybe 30 floors compared to 15 floors. But these are average guidelines. Now, if there's 2 people holding radios, there is a limit as to how far away they can talk to each other. Assuming they're on flat ground, the curvature of the earth will begin to block the line of sight. Sorry, flat earthers. So 2 people 6 feet tall holding a radio, you're only going to be able to talk 6 miles because the curvature of the earth will get in the way. Now, what we can do to increase our range is elevate one or both radios. So now you can see on this graph at the bottom, they raise the transmitting antenna up to 10 feet, and that gets you another couple miles. You go from about 6 miles to 8 miles. Now, let's say we raise it to 50 feet. Now you can talk to someone 13 miles away, assuming the other receiving antenna is only 5.5 feet off the ground. So if we think about this in reverse, where maybe we have a command post and someone out in the field that's only talking at 5.5 feet, if the command post antenna is 50 feet in the air, they might be potentially able to be reached from 13 miles away. So the next thing to think about is there is a horizon and then there is a radio horizon. So you might not need exact line of sight in order to make communication, but you can see the farther away you are from that object, the more space that radio wave has to diffract down. Why does that matter? Well, it might seem counterproductive, but if you're trying to talk to someone on the other side of an obstacle, instead of getting closer to the obstacle, you might want to back away a little bit and give it some space to diffract around that obstacle. But sometimes there's obstacles that are too big to get around, or maybe range is an issue. So we can have something called a repeater. So what a repeater does is it receives the signal and then retransmit it on a different frequency. You can see there's 2 terms here. There's simplex and duplex. So simplex means you're just talking radio to radio on one frequency. Duplex, or a repeater, means that you're talking to a repeater on one frequency, and that repeater then broadcasts that message out on a different frequency. In theory, this allows it to extend your range if you have it in a good position. Now, repeaters do take a little bit of knowledge to set up and require some equipment. You can see on the right side of this page, that is a military repeater. And you can see it just looks like a suitcase. And on the left, that's what repeaters look like sort of in the wild or in the civilian world. Now, this is something called a poor man's repeater. And it's maybe you don't have the knowledge or the equipment to do an actual repeater, but maybe you have an extra team. So maybe team 1 can't talk to team 2, but you send a third team in a position that has line of sight for both teams and is in range of both teams. That third team can listen, write down the information, and then rebroadcast it so that way the other team can hear it. So we talked about radios on the ground. Let's talk about radios in the sky. SATCOM. SATCOM means satellite communication. It typically uses UHF or higher frequencies to communicate between the ground and satellites. Those satellites can then communicate with each other or go back down to the ground. This provides secure long-range communications, but this does require infrastructure, right? It requires satellites. Some examples of this are just our military UHF radios, which I'll talk about in a second, but we also have sat phones like Iridium phones, we have Starlink, and we have the Joint Battle Command Platform, JBCP. This goes by many other names, Blue Force Tracker, but basically it is a awareness program that can communicate through satellites, so that way trucks can talk to command posts over the horizon. So here are some examples of some common handheld radios. On the left we have some civilian radios. The farthest left, FRS radio, that stands for Family Radio Service. That one specifically is made by Backcountry Access. That's common for like backcountry skiers and climbers and things like that. But what the Family Radio Service is 22 predetermined channels. It's always at half a watt, and all the antennas are the same. And the idea is that anybody can buy and use these radios, and because they're all the same power and all the same antenna, you won't have people overpowering each other. So that's a common public radio. The next we have Baofeng UV5R, infamous. These are cheap radios, but it allows you a lot of freedom because you can program these not easily, but there's a lot of things you can program into them. And power goes from 1 to 5 watts. Now these are both analog radios, and we'll talk about the difference between analog and digital later on, but they both have experience being used in warfare, and pretty recently too. It's not something that the US military uses, but it's good to know what's out there and what their capabilities are. Next, we'll get to the first military radio, and that is the PRC-148, also known as the MBITR. MBITR is an acronym for Multi-Band Inter- and Intra-Team Radio, and this can communicate in VHF, UHF, and also SATCOM, which is UHF as well. This goes from 0.1 watts to 5 watts, which is going to be important later. And this is analog or digital. The next one is the Motorola SRX 2200, IISR. I'll skip all the acronyms. This is also UHF and VHF, and this goes from 1/4 of a watt to 6 watts, analog and digital. Now I'm showing this because it's very close to a Motorola APX 8000, and this is something that is used a lot in public service, so fire, police, search and rescue teams, things like that. Again, UHF and VHF, 1 to 5 watts, analog and digital. And then finally, you have like the pinnacle of handheld radios right now, and that's the Harris 152, UHF, VHF, SATCOM, 1/4 of a watt to 5 watts, analog and digital. Now these are radios that people would walk around with, and they talk on UHF and VHF, which means that they have pretty short wavelengths, which means that they can have short antennas, and that's why they're used as handhelds. But what happens when we want to talk beyond our line of sight? Well, like I said earlier, because HF waves have low penetration ability, given the right conditions, they can bounce off the atmosphere and come back down to the ground. So here you can see there's ground waves, which is what you can see line of sight. And then you have the sky wave. The sky wave can bounce up off the ionosphere and then back down to the ground. Now there might be a gap between where the line of sight ground wave can reach and where that sky wave reaches, and that's called skip zone. So HF is typically used to talk to people very far away, but what we can also do in the mountains when there's a lot of obstacles around that blocks our line of sight is we can basically aim the antenna straight up. This is called a near vertical incident skywave, or NVIS. You're shooting the HF signal straight up and it's coming down like an umbrella. So you can see from this graph, when you change the angle that the antenna is pointed, that will change the range at which that skip distance is. Now, the ability for an HF wave to reflect off the atmosphere depends on a lot of variables, and these variables change and can change quickly throughout the day. This makes choosing one frequency to talk on for a multi-day mission unrealistic. The atmosphere changes during the day and at night, and you can see I have a conditions calculator on this slide at the bottom right. And in this example, you can see 80 meters to 40 meters, 30 to 20, 17 to 15, and 12 to 10. They all have either fair or poor conditions for radio waves to bounce off of the atmosphere. So in this case, it is not reliable. These unreliable conditions is why automatic link establishment was created. Basically, the radio operator enters in a number, almost like a telephone number, and that radio sends signals for that specific radio ID, and it'll send those signals on different frequencies, and they will determine which had the best connection between the two radios. And so this takes out having to pull out a phone or check the internet for the best conditions for HF communications at that time. The radios will just test it very quickly between themselves and determine which one is best at that time. So this would be a good time to talk about mobile or man-pack radios. Mobile meaning that it's used in a car, so it's moving around, and man-pack as in like human packable radios, so ones that are typically thrown in a backpack. On the left, we have some civilian radios. The first one is a Yaesu 891 that talks in HF and UHF. You could notice that the power is a lot more, right? 5 to 100 watts. These are typically like plugged into a wall or a car, or people can carry around external batteries. You can see an example on the top left, one that's in a man-pack configuration, and then just under that you see like a cup holder mount for one. So you'll see people, driving around with one, and the antenna is coming out of the hood, just like a typical like radio antenna that you would listen to music on. Now the next one to the right of that is a Xiegu G90, relatively inexpensive HF radio. Now you'll see HF radios typically man-pack or mobile, not handheld, because of how long the antenna needs to be for those big wavelengths. Again, these both come analog, but you can make them digital by adding some accessories to them, and we'll talk about digital later. Next is a radio that goes by many names. I've heard it called a SINGAR, an ASIP, 1523, but these are basically like the standard for vehicle-mounted radios or man packs that I've seen in the infantry. They use VHF frequencies, and they can go down from 1 watt to 5 watts or up to 50 watts with an amplifier in like a vehicle. And these can do analog, and they could also do digital modes, which means that they can be encrypted. And the next is a PRC-158. This is sort of like an updated version of an ASIP. This can do VHF, UHF SATCOM, 1 to 20 watts. Again, you can use the amplifier and analog and digital. Finally, we have the PRC-160, and this is mainly an HF radio, but 1 to 20 watts, analog and digital. So those are radios that either the Army has or you might see in the civilian world. What's the danger? What's the danger of using a radio? Well, one main danger is radio direction finding. So on the left here, you can see a man-packable radio direction finding, a piece of equipment called a Wolfhound. You can see it has multiple antennas on there, and basically it can determine what signal is coming from which direction. On the bottom right, you have a Russian Army electronic warfare truck. Again, it can do many things, and one of them is direction find. And then top right, you have amateur radio Fox Hunt Yagi antenna, so directional antenna, and people actually do this for sport or as a hobby, where they can hunt down specific radio frequencies that other people hide and they find them basically in the wild. So this is how radio direction finding could be used. Basically, you take the bearing from 2 or more locations, and you can pretty much figure out where a radio signal is coming from. And here's more of a military example. This comes from what used to be known as Twitter. Someone tweeted at an Army colonel asking about active camouflage and invisibility cloaks. And he responded with this picture. And his whole point was the fight is no longer visual. The fight is now beyond line of sight. And this is a heat map that they put together of electronic signals captured from 12 kilometers away. And these are electronic signatures from things like cell phones, radios, vehicles, counter IED systems. If you think about what those do, is they are constantly jamming and flooding the space with electronic signals. But those signals go somewhere and can be seen from far ways away. And even active armor, like active tank armor, give off electronic signals. So you can see from this map, radio direction finding isn't something that's hard to do. You can almost see a perfect battalion footprint in the middle of the desert right there. So how do we protect ourselves from this? Whether it's radio direction finding or actually having our communications intercepted by people that we don't want them to intercept? Well, it's called emissions control, or EMCON. And there's 5 points that the Army puts out that can help us control our emissions. The first one is location of our radio. Here I have an example of how to use terrain to mask your signals. So let's say our troop CP is way off there to the right, or the east, and then we have an observation post on the top of this hill overlooking that village. So we have 3 options. If we want to talk back to the troop CP, we can talk on the front of the slope, on the top of the hill, or in yellow on the reverse slope. Here's what the line of sight would look like from the front slope. That's shaded in blue. So you can see if we were on the front slope and I was trying to talk back to the troop CP, the only place that could really hear my radio transmission would be the village and everything to the west. So that's probably not the best place to talk from. Here you can see shaded in red everything that's seen from that hilltop. I can now talk to the troop CP, but that village can still potentially hear my communications. Now, from the yellow, that reverse slope, the village won't be able to hear any communications, even if they were listening to the same frequency I was talking on, but the troop CP can. So what does this mean? This means that when we're doing an OP or something like that, we have a team that's observing the village, and then they come back, give us the information, and then we only talk on the radio from that reverse slope where the terrain is masking our emissions. So the next principle was operating on the lowest power required. So here we have the PRC 152. So we know the output goes from 1/4 of a watt all the way up to 5 watts. And it's also important to remember that changing the power output doesn't necessarily reduce your ability to receive information or receive radio transmissions, right? That depends on your antenna type and where the antenna is and where the radio is. But we can see that at 1/2 watt, flat open terrain, for UHF, the distance is between 1/2 mile and 2 miles. And then as we go up, 1 watt can potentially go up to 3 miles, and 2 watts can potentially go up to 4 miles. And what does this look like on our map? So here, from that reverse slope, 1/2 mile wouldn't quite get us to our troop CP, but maybe we try it first to see if we can. And if we can't, then we bump that up to that 1 watt and see what that gets us. And you can see from this map, in theory, that 1 watt can get us that 1 mile, and troop CP is within that 1 mile. So now we have a quick comparison. From the hilltop, everything that potentially could hear us is shaded in red, versus the reverse slope, and on 1 watt, anything that can hear us from the reverse slope and on 1 watt is anything that's shaded in yellow and within that yellow circle. So there's even one more layer of security we could add to our radio communications, and that's directional antennas. So you can see on the top there, we have things like whip antennas, and just the manufactured antennas that come from a radio. Those are not directional. You can see to the right of that, the radiation comes out in all directions. Underneath that, we have a half-wave antenna, also known as a dipole antenna. Now, these very often need to be improvised and need to be basically handmade, but you can pre-make them knowing what frequency you want to talk on, and then based on what frequency, you know what wavelength you're going to be talking on. Based on the wavelength, you know how long or short to cut those wires. And you can see from the diagram to the right of that, radio waves come out perpendicular to those wires in either direction. One more step even beyond that is the half rhombic antenna. And what that does is that puts it in one direction. And you can see that these are getting more and more difficult to make, but in our scenario, we have the terrain masking us in one direction. So even just a dipole antenna, where we know that one direction it will go back to the CP, and the other direction it's just going to go into the hill and not really be heard by anyone else. And that will basically greatly reduce the area that can hear us. Now, we already have a small area that can hear us, but if you look on the map, there are intersections to the north and to the south that we would be cutting out of the area that can hear us, and that may be important to you, may be not be important to you. So the next principle would be using proper radio techniques. An example of that is ensuring all transmissions are necessary. That's self-explanatory. Pre-planning messages prior to transmitting them. So that's things like writing down the 9 line before transmitting, so that way you're not transmitting longer than you need to. Right? We want to transmit as quickly and precisely as possible, not just so that way other people can understand us on the receiving end, but also that makes it harder to radio direction find because the people that are looking for you would have less information to go off of. And the general rule for that is trying to keep transmissions less than 15 seconds. Something that can help us do that is also using brevity codes or pre-planned code words. The next thing is consider transmitting on the move or changing locations after you transmit. And again, that will reduce the enemy's ability to direction find you, because maybe they can direction find you, but if you transmit and move, you're no longer there. Something that's kind of small but may be helpful to you is avoiding transmitting on predictable schedules. For example, transmitting on every hour on the hour or every half hour. Those are predictable times that people may be trying to listen for you. Finally, data bursts or digital signals can transmit quicker than speech. So to demonstrate this, I'm going to give you an example salute report. Size 3, activity, digging holes, location 11 Tango, X-ray Alpha 1, 2, 3, 4, 5, 6, 7, 8. Uniform, wearing all black. Time 1100 Romeo. Equipment 2 rifles, 1 machine gun. And this is how that would sound with a data burst. So that was an analog data packet, which means that it was using different sounds to represent different characters. But we can do something called digital radio, and basically the sound waves, you can see it on the right better than I can explain it, but the different waves then relate to zeros and ones, also known as binary code, and that becomes digital data. Now that digital data can then be interpreted as voice sounds, and that's digital radio, but it could also be used to share data, and that data can also be encrypted. Now, just because a signal is encrypted doesn't mean an enemy can't see it, but they will have trouble interpreting what it is or what it means. Now, another layer of security you can add is called frequency hopping. This is when the radio changes frequencies or channels many times a second. And if you do this with a wide range of frequencies, it can be very hard to jam because an adversary would have to jam such a large portion of the radio spectrum. And you think about it, if they're jamming that portion of the radio spectrum, they also can't use that part of the radio spectrum themselves. It could also make direction finding difficult, but not necessarily impossible. So here's another example mission using what we know now. We're going to go from LZ Gold down to Viegel and then down to that unknown LZ. So from LZ Gold, you can see there's a hill almost immediately about 500 meters south. So once we get past 500 meters, we won't be able to talk to whoever's back at LZ Gold. So what we're going to do is we're going to set up a repeater to the west right there, and then everything that that repeater can see is highlighted in yellow. So you can see that gives us quite a bit more coverage. So here we have the communications plan for this example mission. And we have the PACE, primary, alternate, contingency, emergency. What this PACE plan does is it gives us redundancy. If our primary doesn't work, then we go down to our alternate. If our alternate doesn't work, we go down to contingency and then down to emergency. You can see here our primary would just be our regular FM, our command net, so to speak, and that's, frequency hop simplex, which means they're talking radio to radio. Our alternate would be that repeater that's to the west. Again, frequency hop, but this time it's duplex because we're talking the repeater. Now there are places along the route where we're not going to have line of sight either to LZ Gold, where our command post is, or to our repeater. And this is where if we absolutely need to get a hold of someone, then we'll be using our Iridium phone. This still enables comms on the move though, which is big because our emergency, our HF, we would need to stop and set up an antenna. And you can see as we move from primary down to emergency, we are trading off convenience for reliability. So being on our command net and talking simplex back to LZ Gold, it's convenient to just try to talk on a radio, but it's not exactly reliable, right? You have distance, you have terrain that's in the way, and there's possible jamming, let's just say. As we go to the repeater, that takes care of the distance problem, so it's a little bit more reliable, but it still has those other problems. And we potentially could still lose line of sight of that repeater. Now the Iridium phone, it is more convenient to use than HF because we don't need to stop and set up an antenna that shoots radio waves, straight up into the sky. We can talk on the move, but the reason why it's less reliable than HF radio is because it still requires an outside entity in the form of satellites. And then HF, you're talking radio to radio, so that's pretty reliable, but it's very inconvenient because you need to carry around an extra radio, and then when you want to use it, you need to stop, set up security, create an antenna that is long enough for the frequency that you want to talk on and is at the correct angle. So that was a short introduction to radios. I'll be getting more in depth with guests that are more qualified than me to talk through some of this stuff. But I think communication is one of the most important skills that doesn't come quickly. So my recommendation would be to volunteer to learn how to fill radios at your military unit or venture into amateur radio. Look into your local radio clubs and repeaters, try to get your license. The test isn't that hard, and it also introduces you to the local radio community. And more importantly, bring radios with you on your typical outdoor adventures like hiking or skiing. Test their capabilities so you know what they can do in your specific environment. If you know someone who this information would be useful to, share it to them. Along with any questions, let me know in the comments what your level of radio knowledge is. Is this your first time hearing this stuff, or is this too basic for you? Those comments will let me know what to talk about next. Thanks.